Okay, so now let's discuss another application of what we have been doing with curves. Up to this point, we have been given the function of trajectory of a particle, and from that you can find the velocity by differentiating once, and then the acceleration by differentiating twice. But you can reverse engineer this process. So from the acceleration, you can also find the velocity and then find the position, but then you have to go backwards, which means that you have to integrate. So again, this is just like an illustration of this fact, which is fairly elementary, which is that if the velocity is the derivative of the position and the acceleration is the derivative of the velocity, then you can also find the velocity as the integral of the acceleration, and then the position as the integral of the velocity. And by this integral, I just mean, as I will show you in a moment, that you just integrate each of the individual components of the vector. So maybe you have already done this example before, but let's say you have you want to describe the trajectory of a body moving under the influence of gravity. So this is like these projectile problems. So imagine that you throw the body from some initial point, and you want to find the position as a function of time. Well, in this case, as you may know already, the acceleration is just a constant called called g, but pointing towards the floor. So that's why I'm putting a minus sign here. And from this formula for the g constant, and from this formula for the acceleration, then you can find the velocity by integrating it. So the velocity is just the integral of the acceleration. So it's just like the integral of minus g j dt. And again, this is just you almost ignore the j for integration purposes. So it's just like integrating minus g dt times j. So j is like a constant. You can take it out of the integral, and so this is also minus. This is just minus gt. But then there's a constant of integration, and okay, so this is where you do need to be a bit more careful, because really what you're integrating is like 0I plus minus gj dt. So really, when you integrate this second term, you get g minus gt, which is what I put here. But when you integrate 0, well, it's like integrating again, like the integral of 0 is just an arbitrary constant, because any constant function gives you 0. So that's this v0 you can think of having like it's not just, it doesn't need to be like a vector just along j. It can also have an I component. So the constant of integration is just really two terms. That's what I'm trying to say. This is like a component in the x direction and a component in the y direction, which is known as the initial velocity, right? So this is the reason why this works is because when you take the derivative of this function, then of this vector function, then you get minus gt, minus gj, which is what you had there. Okay, so the only thing that you have to be careful of is just put like a constant of integration after you do the integral, but just keep in mind that this constant of integration is really a vector. That's what. So what I'm trying to say is that the constant of integration is a vector. It's really a vector of integration. So you just do your ordinary integral, but then you need to do that. And then the position vector is just the integral of the velocity. And so this is just like the same as integrating v0 dt minus gtj dt. Okay? And again, v0 is like a constant here. So the integral of v0 dt is just v0t. The integral of minus gt is minus gt squared over 2j. And again, there's like similar to what happens when you do like an ordinary integral. You add a constant of integration, but now remember the constant of integration is really called vector of integration. So you just add a vector of integration, which is r0. Okay. So in order to write this maybe more clearly, you can just say that the position as a function of time is just a constant vector, which is the initial position, plus v0t. This is what you would, so, okay. Let's just do some interpretation. So if you could turn off the gravity, make g0, that means that the particle would just move on a straight line. That's the equation of a straight line. And so the gravity just adds a bending, right? And in fact, we can find the curvature of this trajectory, which would be fun to do. So the velocity, remember that the tangent vector is velocity over speed. The velocity is minus let's assume that the initial velocity, just to make this faster, well, let's see. Yeah, just to make the algebra easier, let's assume that v0 equals the 0. So it's thrown just from some initial position. Well, no, let's keep it like that's fine. Okay. Okay, yeah, let's do this just for sake of expediency under the assumption that the initial velocity, I don't want to make it 0, that would be too silly, but let's just say that you threw it just with some horizontal velocity. So let's just say that the initial velocity is just has some component in the x direction, but no component in the y direction. That just simplifies the algebra a little bit. Okay? So in that case, the formula for the velocity as a function of time is v0x times minus gt. Right, which is what you expect because the acceleration is completely vertical, so the x component is not changing, so that's why the velocity is time independent in the x direction, and in the y direction is just minus gt. So the speed is just the square root of v0x squared plus g squared t squared. So if I had kept like an initial velocity in the y direction, then this term would be a little bit messier. because there will be a square some squares formula, and it's yeah, it's not something you want to do right now. So the tangent vector is just velocity over speed. And then what do we need for the curvature? The curvature was 1 over speed times the norm of the derivative of a tangent vector with respect to t. Okay, so that's let's see. So we need to find the derivative of the tangent vector with respect to time. So I'll do it this way. In order to differentiate, I'll think of the tangent vector as follows. I'll think of d0 x squared plus g squared t squared to the negative 1/2 times this vector. I think this will be easier for the product rule. So when you find the derivative with respect to time of this thing, is the derivative of the first one, which is minus 1/2 d0 squared plus g squared t squared times the derivative of the interior, which is 2g squared t times this vector plus the other vector times 0 minus g. Yeah, I think that was better. And so there you go. Okay, so if you want, you can still simplify this a little bit more. Yes. Because we need to take the norm, and so you still don't want to take the norm, which with this expression being so messy. So. Yeah, it's a bit of a mess. So I will factorize this, and then if you do factorize this power, you get minus 1/2 of d0 squared x plus g squared t squared, and then there's a 2 that got cancelled here, so you get minus g squared t over d0 squared plus g squared t squared times d0 x minus gt, and then plus 0 negative g. Okay. Whew. And then finally, so wow, so even in this problem, you can see that finding the curvature is not entirely trivial. So So again, this is a common factor multiplying everything, and then I will combine these two into a single vector, which will be the vector minus g squared t v0 x over v0 x squared. Oh, okay. Yeah. I think I'll do common denominator as before. So as I have done in the past, so this will become this, and then this will be minus g squared t v0 x. Then this becomes g cubed t squared, and then when you do common denominator, this becomes 0, and then this you multiply this here, so you get minus g v0 x squared, and then minus g. Oh, beautiful. So good. It's not looking that bad now. So finally, you get, hopefully I didn't make any stupid mistakes, you get the derivative of the tangent vector is v0 x squared plus g squared t squared to the negative 3 halves times the following vector. So you add them component by component, so you get minus g squared t v0 x. And then this, when you add them together, these two cancel, so you get minus g v0 x squared. And so the norm of this vector, notice that you can factorize g v0 x, and so when you do that, when you factorize that, you get this thing, and yes, in fact, you could even factorize a negative sign. So good. And now finally, the norm of this vector is just the norm kills the negative sign, so you just get this term. You get g v0 x. This is this term. This goes to the denominator if you prefer. So this becomes v0 x squared plus g squared t squared to the 3 halves, and then this becomes square root of v0 x squared plus g squared t squared. Oh, good. So there's some further simplification. And so the norm is just g v0 x over v0 x squared plus v squared t squared. Okay, and then the curvature. Remember, so does this have? Okay, so the curvature has to be 1 over speed times this thing. So it should be 1 over speed. So 1 over. I mean, it would just give you g v0 x over this thing to the 3 halves. So let's think about it for a second. At least, does this have? Remember, curvature is supposed to have units of 1 over distance. So what are the units of this? The units of this have units of acceleration times speed is length squared over time cubed, right? And this has units of length squared over time squared. When you take the square root of that, you get length over time. And then you cube that, and so you get time cubed over length cubed, so you get 1 over length. So this has the right units. So this is your formula for the curvature. So it was important to have an initial velocity in the x component so that there was non-trivial curvature. And you can see how it depends on t. So as t goes to infinity, the curvature goes to 0, for example.